Hello, everybody. My name is Rodrigo Moreno, and together with Diego Alvaro, Alexandre Street, Mathaios Panteli, Pierluigi Mancarella, and Goran Strbac, we have prepared this presentation entitled A Distributional Robust Optimization Approach with Decision-Dependent Ambiguity Sets for Planning Resilient Network Investments. So this presentation is about planning networks against natural hazards. So the context of the presentations is precisely on natural hazards and mentioning that this actually threaten the integrity of power system across the globe. We have seen catastrophic consequences of these natural hazards, and in here I'm just presenting two examples. And one of the examples that I like is the 2010 earthquake in Chile that caused a major blackout that affected 90% of the population. Was actually full blackout of the main transmission system that affects this much of the population. And considering that the frequency and the impact of these events is actually increasing because of climate change, and I'm not talking about earthquakes, I'm particularly talking about a climate-driven events that has these catastrophic consequences on the network. So given this context, we think that planning resilient network investment is becoming increasingly important. So the problem is designing, planning resilient network investments. We need to consider in this problem that we want to install new infrastructure. And this is a classic problem of network investments. But also we want to combine this new infrastructure with other sort of decisions like hardening existing infrastructure, making infrastructure less fragile against natural hazards by, for example, undergrounding, anchoring substations, and in general, taking decisions that will make existing infrastructure less fragile against hazards. And also, we want to consider the uncertainty associated with the fragility curves model. I will explain to you in a minute what is fragility curves, but the fragility curves is an actual model used to model fragility in network infrastructure. We basically translate the intensity of the hazards into probability of outages through these curves, but the assumptions used for building these curves are very theoretical, and this may not really apply in different cases in practice, and we want to capture this in our model. The usual way to do this would be through stochastic programming. So through stochastic programming, we manage different levels of uncertainty, usually associated in this case with natural hazards and the outages provoked by these hazards. And then with this stochastic model, considering this uncertainty, you would take decisions. But there are two major problems with stochastic programs. The first one is that hardening decisions is very challenging. And this is because you have decision-dependent probabilities. In this case, we want to make network infrastructure, as I said, more robust, less fragile against natural hazards. So when we actually reinforce or harden a given asset, we want to make the probability of outages smaller for this very particular equipment that we have hardened. And this is fundamentally, as I said, problematic within stochastic program. And the second one is that stochastic program assume perfect information of probability values. And this is a problem in this case, especially when we considering the model fragility curves, which, as I said, is a quite theoretical tool, which is being applied in practice, and there is a lot of uncertainty associated with the accuracy of these curves. So to basically overcome this problem, we propose a distribution robust optimization, mainly because of two reasons. The first one is because decision-dependent probabilities can be treated in a very straightforward way, as probabilities are already endogenous decisions in distribution robust optimization. And secondly, because we can associate ambiguity levels to these fragility curves. And by capturing or by reflecting the fact that we have some uncertainty, in this case we would say ambiguity because it's referring to probabilities, we can actually reflect or capture the fact that there are some accuracy problems associated with the fragility curves. So we have a model, we propose a model with the following scenario tree. We have investment decisions in the first stage. We also have a pre-contingency operational decisions in the first stage. And then we have a second stage in which we have post-fault or post-contingency decisions in operational timescales. And here we manage two layers of uncertainty. The first one is related to earthquake scenarios, and the second layer is associated with contingencies and the corrective control associated with those contingencies. And the probability of the contingency is conditional to the earthquake which is being modeled, and this is an important consideration that we will study later on. So the mathematical formulation is a cost minimization in which we have cost of operation. In this case, we have pre-fault operation, post-fault operation. So these are the pre-fault operational decisions. We also have investment decisions associated with expanding the network, new lines, new assets, which is this term. And also we have hardening decisions, which is making existing assets more robust or less fragile against natural hazards. And because this is distribution robust optimization, we have this term, which is basically reflecting a worst case expectation of post-contingency costs. In here we are optimizing over probabilities, and this is the decision-dependent ambiguity sets. And as I mentioned before, this is associated, this XH associated with the hardening decisions. So decision-dependent ambiguity sets looks like this. This A is the support that contains all the contingencies. The A refers to availabilities of a given asset in a given scenario and time. We also have the expected, or let's say upper and lower bounds for the availabilities of these assets. And we also have this term reflecting the fact that we may harden some of the infrastructure. Therefore, K is the matrix that contains the information about the changes in probability when we harden the given assets. So in here we can construct by choosing S and mu, we can construct intervals for the expected availability of network assets. As I said before, we have fragility curves. Fragility curves are curves usually coming from civil engineers that relates the intensity of the hazard and the probability of having a fault or an outage in a network equipment. So how this works, for example, in this case, we have PGA in the x-axis. PGA means peak ground acceleration. This is a fragility curve used for earthquakes. So the higher the acceleration of the ground, of course, going to be the higher the failure of the equipment, which is subject to that acceleration. So these curves are relating this failure probability with the PGA. As I said in the beginning of the presentation, these curves are quite theoretical. So we would like to have an ambiguity level, let's say, for these curves in order to make it more practical and reflect the whole uncertainty associated with the curves. So we have 3 fragility curves. Let's say we have a central fragility curve, which is related to, let's say, the expected value of failure probability for a given PGA, but we also have upper and lower bounds, which are related to the interval defining the ambiguity. When we harden a given infrastructure or a given substation line, we shift these curves to the right, meaning that the equipment is less fragile. And this is exactly what we call the decision-dependent probabilities, because these failure probabilities are actually changing when we take hardening decisions. And this is reflected here because we're moving this curve from left to right, making the infrastructure more resistant against natural hazards, in this case, earthquakes. We use a bilevel approach to solve the problem. So we have a cost minimization in the first level, and we have in the second level a maximization of expected costs. In here, we are optimizing on the value of probabilities to find what's the sort of this sort of worst case scenario for a given natural hazard. So we tried this model on for busbar representation of the Chilean system. We have several earthquake scenarios. We also have, we try the model and we run sensitivities for different ambiguity levels. We have different candidate transmission assets for expanding the network. But more importantly, we have also assets that can be hardened. So we will find an optimum portfolio between adding new infrastructure in the network, but also hardening existing infrastructure and making it more resistant against earthquakes. And as a third option, we can also include in this portfolio of optimum network enhancements, we can combine them with DER, distributed energy resources, that can provide security service on the main load centers. So the first set of results illustrate the importance of hardening decision, how we can combine these hardening decisions with expansions in the network. So in here, we have in the y-axis, we have the number of enhancements in terms of substation, hardening decisions and new lines. I'll show you what all these numbers in the x-axis means. So 10, 30, and 50 means the different ambiguity intervals for the fragility curves. And alpha is a value that multiplies a reference earthquake probability, which in this case is 1.2%. So for the last case, 100%, in here we reflect the fact that an earthquake may happen with a probability of 1.2%, but in the first case, we have zero probability of earthquake, and we have all these cases in between for different values of alpha. So the first thing we can observe is that in this particular case study, if there is zero earthquake probability, we do nothing. We don't really need to invest. So all investments in this problem are because of earthquakes and because we want to hedge against the risk associated with them. So while we are increasing the value of this probability of earthquake, you see that the models start hedging against those natural hazards. The first move is hardening substations, but when you start increasing this probability, you start combining the hardened substation with new lines. Importantly, when you have a higher ambiguity level, there are also some investments, meaning that investments in these worlds are not only to hedge against the risk associated with outages and the natural hazards provoking those outages, but also to hedge against ambiguity, hedge against the uncertainty of partial information regarding reliability data coming from this fragility curve. So because we don't know exactly how this fragility curve looks like, we're going to take some decisions which are going to also hedge against those risks. Another set of case study we run is similar studies as before with different earthquake probabilities and different ambiguity levels, but now we run the model with hardening decisions and without hardening decision. Without hardening decision means that the model can only install new infrastructure, new transformers and new lines, which is the classical model for transmission expansion. And in here, what we can observe, and I want to call the attention for case 3 and case 5, then when you have a classical approach, which is without hardening, you will make investment decisions, in this case, adding new lines in the system. So for example, for case 3, adding 1 line, or for case 5, adding 3 lines, you will make decisions that are not made under the fully blown model that consider hardening decisions. So for example, for case 3, if you have the possibility not only to add new infrastructure in the network, but also harden, you will actually prefer to harden substations, in this case 5 substations, and this will save the installation of this line, which is fine by this, let's say, incomplete model without hardening decisions included. So this illustrates the importance of modeling both network expansions in the sense that we are talking about when we say expansion of new lines, but also of hardening existing infrastructure. And actually hardening existing infrastructure is a quite promising and a good measure to deal with natural hazards. In this case, for example, earthquakes, we see that hardening substation is quite an important measure to hedge the system against blackouts. So some remarks at the end. We propose a model that finds the optimal portfolio of resilient network investments, recognizing the ambiguity associated with fragility curves and capturing hardening propositions through decision-dependent probabilities, which is, as I said in the beginning, is quite a challenging problem. Secondly, we demonstrate the importance of substation hardening decisions to enhance network resilience against earthquakes, combining these hardening decisions with DER services and also new network assets. And number 3, we also show how resilient network portfolios can serve to hedge against the ambiguity of fragility data, highlighting the need to recognize such ambiguity and reduce it through better fragility models. So I'm giving you here a few papers. The papers number 2 and number 3 are already published, and we're trying to publish this new paper, which is the core material of the presentation today. Thank you very much.